Am I? Yeah. Um, so the idea was write the equation of this plane, which is what? Which contains this line, and that's the parametric equation of the line, and it's parallel to this plane. Last time, the way I did it, I kind of what? Picked a point on the line, then I picked a general point on the plane, called it px xyz. Then I formed this vector because the planes are parallel. So the normal vector for this plane is exactly the same as normal vector for this plane. As a matter of fact, it's a scalar multiple of it. Let's pretend the scalar multiple is 1, okay? So this is what I did. Because the normal vector, by definition, is a vector which is perpendicular to any vector on the plane, so I took that vector, P0P, I dotted with what? Normal vector, which is the same as the normal vector for this guy because the planes are parallel. And lo and behold, I got the equation. What I'd like to make a note is I didn't have to pick what? A general point on the plane. I could have just used this point, which happens to be on the line, but the line is on the plane, therefore the point is also on the plane, and use this normal, and then use what? Point normal form, and still you get the same equation. Do you see it? So this, think of it, this is method 1, that's method 2. So in other words, pick a point on the line, right? You know the normal, you know the point. Remember that point is on the line, but the line is on the plane. So you got a point, you got a normal, use the point normal form. You know what that is, don't you? It's kind of like a times x minus x0, b times y minus y0, plus c times z minus z0 is equal to 0. Whereas the point in this case is what? X0, Y0, Z0 is 308, and ABC is what? 248, which happens to be the components of the normal vector. Do you all see it? So think of it as two ways to get to the same answer. So I just want to quickly mention, so in case you have to find, you know, the solution for this kind of problem, there are two ways to do this, okay? Is that all right? Is it okay? Does that make sense? Yeah. Uh, so last time we graphed what? You know, one out of 6, I believe, quadric surface, and that was namely what? Elliptic paraboloid. So remember, this is like 12.6. The whole idea behind this section is how do you graph quadric surfaces. Quadric means what? Second degree polynomial functions in 3 variables, x and y and z, right? Remember I showed you last time that these guys have a kind of like a very long what? Equation. And so the idea is, how would you graph some of these equations? At the moment, I can't find it, but you know how that goes. Remember, ax squared plus by squared plus cz squared. Then you have what? Powers of 1, like let's say dx, dy. You know, it goes all the way, and then you have a constant equals 0. So that's general form of a quadratic what? Equation in 3 variables, okay? Then you also have what? XY term, YZ term. It's a huge equation. So last time we talked about what happens if you have this kind of equation, like, you know, Z over C, x squared over a squared, and y squared over b squared. So remember, C and b and a are pretty much constant, correct? If you recall, last time we kind of decided to what? Find a projection, like the example I did was x squared over 4 plus y squared over 9. Do you remember? So what we had to do was find the shadow of this surface projection on the what? YZ plane, do you recall? Projection on what? XZ plane, projection on XY plane. So we can get an idea how the cross section of this surface looks like. So that hopefully will help us to what? To graph the surface. So if this is my three-dimensional axis, so let's say I'm going by right-hand rule. So this is like y-axis, x-axis. On the YZ plane, you all know the equation is what? This guy. In other words, if you would graph this in YZ plane, the graph would be a parabola. In XZ plane, the graph would be parabola as well. So there goes its equation. However, in XY plane, the graph is a point. Okay? So if you would graph these parabolas like so, okay, I'm just graphing it for you. So one of them is this guy, the other one is this guy. Here it is. But now the question is, what would happen if I cross this what? Cross this so-called surface with a plane equals, let's say, z is equal to 1. You know, somewhere out here, what curve would be the intersection of this surface with the plane? How would that curve look like? Remember, the intersection of two surfaces happens to be a curve. Well, that means you go back to the equation right here, replace the z with 1, and you get this. Do you all see it? This is kind of one of those conic sections. The denominators don't match, so the graph, I would say, it's kind of like an ellipse. So, therefore, somewhere out here, I will try to graph an ellipse like so. Do you all see it? So that kind of sort of how this guy looks like, and this guy has a name. It's called elliptic paraboloid. Elliptic paraboloid. So if what the denominators are equal, then we would call this circular paraboloid. Remember, loid means like. So that means it's like a parabola, but it's not a parabola. Parabola is a curve, but this guy is a surface. Do you all see it? Yeah? Are we okay with that? Everyone? Anyone? Questions? So we good? Everyone sees it? We had one more page. I'm not sure where I put it though. The next one is called ellipsoid. So the next graph is called ellipsoid. Okay. Ellipsoid, as you can tell, it's like an ellipse. It's like a football. And the equation of the ellipsoid is like, let's say, x squared over 1 plus y squared over 9, let's say, plus z squared over 4 is equal to 1. Notice the denominators are not equal, therefore the graph is called ellipsoid. If the denominators were equal, you know, special case, what would you say the name of the graph would be? Suppose the special case of that equation is when the denominators are identical. Let's say they're all equal to 1. What is that equal to? Does anyone recognize that?
Is that a sphere?
Exactly. So what we're saying is the bottom line is sphere is a special case of ellipsoid. Ellipsoid, the denominators don't match, but you still got pluses, you still got the squares, and you still got a 1 here. This is called standard form, correct? Standard form. Okay. So sphere is a special case of ellipsoid. So how do you do this? Well, once again, you find a projection on each plane, such as YZ, XZ, XY. You remember to find the projection, remember projection means shadow. So that means if you would what? If this is your, let's say, three-dimensional axis, when I say find the projection, what? Of the surface on YZ plane, what you're doing is you're shining the light, what? Through the x-axis. If I say what is the projection of the surface on xz plane, you're shining the light through the y-axis. And when I say what's the projection of the surface on xy plane, you would shine the light through the z-axis so you can see the shadow on the floor. So that's basically projection is. In layman terms, it means if you shine a light, how would their shadow look like on this wall, and the floor? Remember, this is the corner of the room. So turns out on YZ plane, I have y squared over 9 plus z squared over 4 equals 1. On the XZ plane is x squared plus what? Z squared over 4 equals 1. And on XY plane is x squared over 1 plus y squared over 9 equals 1. In other words, it looks like I'm getting a bunch of ellipses, okay? So let's do the first guy. So the first guy, if you set the numerator to equal to denominator and set what? Let me just put it this way. If you set z is equal to 0, that would give you the what? Y-intercepts of this ellipse, which is a curve. If z is equal to 0, y squared equals 9 because you can multiply both sides by 9. So y is equal to plus or minus 3. So there. And similarly, if you set y equal to 0 and solve for z, so that will be z squared equals 4 because you can multiply both sides by 4. And that will give you like what? Z is plus or minus 2. So you get this. You see it, which is an ellipse. Okay. You know why we came up with the curve, right? Because we took the surface and what? Find the intersection of this surface with what? With x equals 0. What is x equals 0? It's not a point, it's not a line, it's a plane. It's the coordinate axis, this guy. Okay, so the intersection is an ellipse. Similarly, like here, so you go plus or minus 1, but z is still equal to what? Plus or minus 2. So you kind of get this guy. Okay, that takes care of that guy. Finally, this guy is what? Y is plus or minus 3, but x is plus or minus 1. So I'm already there. So it's kind of like there. So this would be like the graph of a what? Of an ellipse. How does it look like? It looks like a football. So sphere is a special case of what? Football. But we don't call it football, it's called ellipsoid. You know, it's a surface which looks like an ellipse, but it's not. This is three-dimensional what? Surface. Ellipse is a curve, but this guy is what? Is a surface. Just like sphere is a basketball, correct? Here is a basketball, correct? Okay, we call this in mathematics a sphere. But circle is what? When you cut this basketball and take a look at what? Cross-section or ellipse. So those are curves, but the whole basketball is not a curve, it's a surface. So that's what we are talking about. Do you all see it? Any questions so far, guys? Yes? No? Maybe? Any question? Okay. So the next idea, or the next graph, there are like 6 of these guys, is this guy. When you have z squared over what? C squared, x squared over a squared, plus y squared over what? B squared. So notice, it's almost the same as elliptic paraboloid, except elliptic paraboloid had one z on the left, but this guy has z squared on the left. But the right side looks like elliptic paraboloid. Believe it or not, this is cone, a circular cone. Let me give you an example so you guys can see what we are talking about. Just suppose you get z squared equals x squared over 9 plus y squared over 4. So remember, in this case, C is equal to 1, A is equal to 3, and B is equal to 2. Do you all see it? Okay, so what do? I find the projection, right? I, project this surface onto two walls and the floor. Specifically, XZ plane, YZ plane, and the floor, which is XY. When I say projection, that means what? The cross-section of this surface with the plane is y equals 0, the plane x is equal to 0, the plane z is equal to 0. So these are coordinates planes, right? So the intersection of two surfaces is a curve. For instance, in xz plane is this, is x squared over 1 equals x squared over 9. In yz plane is z squared over 1 equals y squared over 9. Is that a 4? 4. And in xy plane is what? X squared over 9 plus y squared over 4 equals 0. So the question is, these are the curves, these are the intersection of the surface with these planes. Remember, these are not lines, they are not point, they are planes in 3 dimensions. So what are these? Well, if you solve this for z, you get plus or minus 1/3 x. This guy is z plus or minus 1/2 y. And this guy is the only equation, or how would I say, ordered pair of xy which satisfy this is the origin. In other words, it has to be 0, 0, because when you add two numbers, square them, add them up, come up to 0, they have to be 0, 0. So, believe it or not, the equation, the graph of these guys on x, y, and yz plane, they are just a bunch of intersecting lines. So what's happening is this, folks. So what happens, let's say I have z plus or minus what? 1/3. So here's one, here's the other guy. So these guys will be like z is equal to plus or minus 1/3 x, which they go through the origin. I don't know if you guys can see it. On the other hand, for the other guy, I also have the same deal. So this would be like what? This guy, and let's say this guy. Okay, there. And this would be like z is equal to plus or minus 1/2 y. So remember, the intersection of these planes with the surface is what? Two intersecting lines. Okay? So now the idea is, well, what would happen if I go on the plane plus or minus 1? In other words, I'd like to know what happens to the surface if I intersect it with what? Z is equal to 1 plane and z is equal to -1 plane. What would be the intersection of the surface with these two planes here and here? Okay, remember, these are not points, these are planes. Turns out, if you replace the z's in your equation right here with plus or minus 1, in both cases you get 1 equals x squared, what? Over what? 9 plus what? Y squared over 4. Whether z is plus or minus 1, because it's a squared, you still get 1. Do you see it? And what is the graph of this guy in what? On the floor? Looks like it's an ellipse. So I get an ellipse here, and I get an ellipse here. Ladies and gentlemen, this would be like what? A circular what? Parabola. This would be a circular cone. Do you see it? Any question on this one?
Professor, I got a quick question about this one.
Yes, please.
So you said it would be a circular cone, but the cross section.
I meant to say just cone. It's not circular. You know why?
Okay.
Because the denominators don't match. My apologies.
Okay. And
If
then
the
if they,
denominators, yeah, if the denominators were identical, then it would be circular cone. But
okay.
this is not circular. Yeah, thank you. I apologize. Yes. But do you see how it's graphed? As I mentioned last time, I really don't expect anyone to become like an artist or anything, but at least know how the basic graph looks like. So later on, in later chapters, we're going to find the cross section of these guys. We're going to find the volume of these surfaces. We're going to find the surface area of these surfaces. So it would be nice to know how they look like. So at least we have a vague idea how to set up the integrals, like, the limits of integration. Because if you don't have the graph in front of you, it's extremely difficult to tell which limit goes on top of which integral. Specifically when we talk about double integrals and triple integrals to find the volume and stuff, not to scare anyone, but basically it would be nice, at least you have an idea how the graph looks like. So it won't be like, you won't answer the question just by flipping a coin. So you have an idea how to approach the solution. Do you see it? Let me see if I have any chat address to me. Also, that would be a sphere. Yes. I'm really bad at drawing. Well, let's join the club. It is not about drawing. It is just like when you take a statistic class and when they get to probability, you know how they play. Some of the problems have to do with deck of cards. Immediately students tell me, well, I don't know how to play cards. Well, neither I do. I don't either. But the idea is not about drawing, it's about what? Knowing how the picture of these guys look like. At least you realize by now that we finished this, hey, this kind of equation is a cone. Incidentally, these are not written on stone. What if I change the equation, let's say, to this? X squared over 1, let's say, y squared over 4 plus z squared over 9. Now what? In other words, I don't want you to think this is it. That's not it. There are a variety of variation of this equation. So if I had this, what would you say the equation, the graph might look like?
It's still a cone, but it's just on the x-axis.
Excellent, excellent. So thank you so much. Appreciate. So still a cone. Very nice. Still is a cone, but now these guys opens along the x-axis. By the way, there is an old-fashioned name for these guys. It's called the nap. Oh, I don't know, it's nap or nape. So this is like upper nape. This is the lower one. So these are called NAPPE. I don't know how you pronounce it. Is it nap or is it nape? So there you have it. Now you know. So this is upper and this is lower. As a matter of fact, if I had this equation, notice I'm just showing you a variation of this equation. What if I had this guy? C is equal to plus square root of, I don't know if you guys can see it, square root of x squared over 9 plus y squared over 4. What would you say the graph of this guy is? Remember, I just took that guy and took its square root. What do you think? I'm sorry. Yeah, that would be like this guy. So it would be upper half. So you don't have to graph the lower half. The lower half would be z is equal to minus square root of x squared over 9 plus y squared over 4. That would be this guy. So notice I took the equation, I kind of manipulated it, and I wrote it this way. But technically, the answer should be plus or minus square root of x squared over 9 plus y squared over 4, but I took the plus. So what does that tell me? That tells me I'm dealing with the upper half of the cone, not the lower half, because the lower half has a minus sign. Do you see it? So keep that in mind. and then we will go from there. Yeah, any questions so far? Let me see if the chats are addressed to me. I just looked it up and it pronounced like nap. Yeah, that's what I thought. I did too. Thanks, Nick. Yeah, yeah, I Googled it. It's nap. But boy, it just spells, it really spells crazy. Okay, yeah, it's like taking a nap, I guess. So that's old word. So that's that guy. So the next guy is this, is x squared over a squared plus what? Y squared over b squared minus z squared over c squared equals 1. Notice everyone has a power of 2. It almost looks like a what? Ellipsoid, except one of the variables has a minus sign. Do you see it? So the name of this particular what? Shape is called hyperboloid. Hyperboloid of one sheet. Okay, because we also have hyperboloid of 2 sheets. So this would be 1 sheet. It's basically going to look like what? A nuclear plant like this. Do you see it? Okay. So let's hit one example and see how would you go about graphing this. Let's say I got x squared over 9 plus y squared over 4 minus z squared over 25 equals 1. So it'd be nice if I identify what the name of the graph is, how it's going to look like, so I can work my way towards that graph. So it won't be like I'm graphing this blindly. So I know ahead of time the graph is called hyperboloid of one sheet, just like in algebra classes when I gave, when you were given this, you didn't wonder, oh my God, is it going to come up as a line or a curve? Well, you knew ahead of time it's a parabola. You just did it, right? Either you did it, what, algebraically, you know, at the algebra level, or you did it at the calculus level by finding the derivative and finding whether the graph increases or decreases, all that good stuff. So the bottom line is, it would be nice to identify the equation. You know, what is it called? How does, you know, a hyperboloid of one sheet look like, so I can work my way towards it. So the usual projections, so let me just stop writing so you know what these projections are. So one of them will be x squared over 9 minus z squared over 25 equals 1. The other guy will be y squared over 4 minus z squared over 25 equals 1. Can you all tell me, or someone please, if I happen to be on xz plane or what? A YZ plane, how would these curves look like? Remember, these are not surfaces anymore, they are curves. Does anyone recognize these equations?
They're ellipses.
Well, ellipse has a positive,
Oh, yeah, you're right.
right? So these
Those
are
ones would be hyperbolas.
hyperbola, correct. So because x appears first, so the branches of the hyperbola opens along the x-axis. And here, the branches of the parabola opens along the y-axis. Depending on which variable shows up, because you have a minus, so they are not ellipse. Ellipse has a plus. So these are like called hyperbola. Hyperbola. But this is a curve. It's on the floor, but these are in a space. So what I'm going to do is I'm going to go ahead and what? Draw my good old what? Three-dimensional coordinates axis. Okay. Now I'm going to graph these guys. How? To graph these, I need to find, remember these guys were called, what were those dotted lines called? Remind me. Anyone? You know, from
Asymptotes.
asymptotes. Okay. And I know how to spell this, but you don't pronounce the P, right? It's asymptotes. And what are the asymptotes? Those were the guidelines. You know, like the traffic cones, you know, Caltrans people put on the freeway. So, you know, cars, you know, so they won't fall into a pothole or something. So those are guidelines. So that's what they are called, asymptotes. So let me find you the asymptotes so I can graph these branches. Here's what you do. First, set each numerator equal to its own denominator. So x squared equals 9. So x is equal to plus or minus 3. So you go 1, 2, 3. 1, 2, 3 there. Do the same thing for z. Set the numerator of this second fraction equal to its own denominator. So z squared equals 25, so z is plus or minus 5. 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. Now make a box, okay? So from the z-intercepts, I draw the box parallel to the x-axis. Okay. From the x-intercepts, I draw the lines parallel to the z-axis. So notice my box is tilted. It's not straight. Okay, so there goes my so-called auxiliary box. So what's so good about this box? Well, if I connect the diagonals of this box, okay, like so, going through the origin, like so, guess what? Those are my asymptotes. Okay, that's how you find or graph the asymptotes in 3 dimension or in 2 dimension as well, 2 dimension. Let's see now. This was about this guy. X showed up first, so the branches of the hyperbola is going to open up along the x-axis. Watch this. Here is one. Here is the other one. Do you see it? I gotta do this guy. Okay, that guy requires a different auxiliary box. The name is auxiliary box. Okay, this guy is called auxiliary box. So now I need auxiliary box for this guy. So set the numerator equal to its own denominator. So that would be y is equal to plus or minus 2. So here is 2, here is 2, and z is still what? Plus or minus 5. Now I have to make box with these 4 points, these guys. Okay, so what do? From the y-intercepts, draw lines parallel to the z-axis, like so. Okay, like so. From the z-intercepts, draw the lines parallel to the y-axis, like so. There goes your auxiliary box. Do you see it? I did it with black. I hope you can see it on your monitor. So now, guess what? Y shows up first. Can you all see it? Y shows up first. Where is it? It's right here. So therefore, the branches of this hyperbola is going to open along the what? Y-axis. But wait a minute, you didn't draw the asymptotes yet. You are absolutely right. So let me just draw the asymptotes. So here is one, and here is the other one. What are you doing? Connecting the diagonals of the auxiliary box. So that will tell you how wide each branch is. So here is one of them. Okay, remember you got to get as close as possible to the asymptotes. Here is the other one. There you go. Do you see it? Now I gotta what? Top these guys up. I gotta put a lid on these. So what do? I kind of sort of go, hey, what happens at z is equal to 1 and z is equal to -1? In other words, if I go back to the equation, replace the z with plus or minus 1, how would the intersection would look like? Okay, let's say that's plus or minus 1. I'm just making that up. So looks like if you replace the what? z's with plus or minus 1, you get x squared over 9, y squared over 4 minus 1 over 25 equals 1. So you get x squared over 9, y squared over 4 equals what? 26 over 25. Okay, I don't really care about these numbers. I just want to show you, hey, the graph is still as an ellipse. So draw the ellipse then. So here is one of them, and here is the other one. Ladies and gentlemen, this is called elliptic of one sheet. Excuse me, hyperboloid of one sheet. Do you all see how this comes about? Do you see it? So it's called hyperboloid of one sheet, which looks like a nuclear plant, doesn't it? So there you have it. Do you have the same picture? I wish I could see your graphs to see how yours look like. This is as good as mine gets. How does yours look like? Does anyone dare to show the graph? The P and E are just silent letter. Yes, yes, correct. Yeah, anyone would like to share their screen? So please show your graph so we can see how your picture look like. No? You mind showing us? Anyone? Just want to know how your picture looks like. Is it better than mine? If it is, I'd like to see it, because then I can copy your graph. Oh, I can't screen share. No, I know. I was just going to say, if you you know, kind of unmute your video so you can kind of put your graph next to your camera's lenses so we can see. I don't have that. Yeah, that's okay. That's fine. I was just wondering, that's all. So
That's
we
right.
good?
I can show mine if you want.
Yeah, Nick. Could
So
you?
the only thing is I didn't draw the asymptotes in the boxes.
Uh-huh.
It was more just like a sketch. So there's a,
I see it.
and
I
then
see it.
I actually have another one too. This one got very, very like hectic because I drew it too small.
Uh-huh.
A lot
I
of
see it. I
time.
see it.
Yeah, it got
Yeah.
very, very like,
Yeah, they got out of control,
yeah.
the branches of the hyperbola. I see it. But thank you. Thank you for sharing your picture with us. I sure appreciate. Hey, it's just as good. But you know what, Nick? Make sure these guys look like an ellipse, not a circle, you know? Then it will look like a cylinder, you know? So make sure these guys are like an ellipse, you know, like an oval shape, you know, like this, not like this. Otherwise, it will look like a what? Like a long what? Kind of like, what is this? Like a cylinder. But anyways, thank you. Thank you so much. I really appreciate. Okay, the next one is, you guessed it, it's called hyperboloid. Hyperboloid of two sheets. Okay, so the equation of this guy is z squared over c squared minus x squared over a squared minus what? Y squared over the what? B squared equals 1. So instead of 1 minus, now we have 2 minus signs. Do you see it? But everyone has a power of 2, and you still have 1, so this is called standard form. Standard form, correct? So I will do my usual projections just to see what's going on here. So on the xz plane, I will have z squared over 4 minus x squared over 9. On what? YZ plane, I would have what? Z squared over 4 minus y squared over 1 equals 1, right? And then on the xy plane, I would have x squared over, what was it? What was the equation? Oh, I'm sorry, didn't I give you the equation? My apologies. The equation is z squared over 4 minus x squared over 9 minus y squared over 1 equals 1. Sorry, I thought I gave you the equation. That was the general form. There it is. Okay, so if you find the projections, you get x squared over 9, what? And plus y squared over 1 equals -1. All right, so if you set this guy equal to 0, you get this. But if you multiply both sides by negative, so these guys become positive, but the 1 becomes negative. But because you're squaring what? Two numbers, the sum of the square of two numbers cannot be what? -1, so there is no cross section here. So no cross section. There is no shadow on the floor. Do you see it? Because this doesn't make sense. When you add two positive numbers, you can't possibly come up with -1. You see how I came up with -1. When you set z is equal to 0, you get this. Multiply both sides by negative, these guys become positive, but the 1 becomes negative. But it's impossible to add two positive numbers and get a negative, so no cross section. But here you have two hyperbolas. Hyperbola, hyperbola. And they both open along the z-axis. Do you all see it? So basically, so just to save some time, so, and if you draw the boxes, so these would be your, one of your asymptotes. The other asymptote will be just like this, except it crosses what? These guys on different spot. But in both cases, the branches open along the what now? Z-axis. Do you see it? So, so what else? So now I have to do the branches. So, how would the branches look like? They will look like this. Okay, there. Do you see it? But wait. Whatever happens to up here and way down here, okay? Let's say you're at, I don't know, z is equal to some number like, let's say 3 or -3. I couldn't use 1 because the, what? How would I say this? If you use a number less than 3, that will not work. For instance, if I say z is equal to 2, notice that would be like what? 4 over 4, which is 1. So I get like this. Excuse me, guys. I get this. And 1 cancels 1, I get what? A point. So that doesn't really cut it. So I need to get what? An answer greater than or equal to 3. So that's where the 3 is coming from, somewhere out here. So it has to be inside the branches, not outside. That's the bottom line. Anyways, if you select 3 or plus or minus 3, believe it or not, you're going to end up with x squared over 9 plus y squared over 1 equals 5 over 4. How did you get this? I selected what? Z is equal to plus or minus 3. So I went back to the equation, replaced the z with plus or minus 3. This is what I got. But you recognize this is the graph of an ellipse. So I would have an ellipse here. Here's one. And here is the other one, guys. There you go. Okay. So now, ladies and gentlemen, this is called what? Hyperboloid of two sheets. It's kind of like two satellite dish, but they open opposite direction. Do you see it? Yeah. So this is called hyperboloid of 2 sheets. Okay. Do you all see it? I don't say they are easy. The idea is identify the graph. But if you remember last time, I said that 3 important graphs which shows up over and over in upcoming chapters is the graph of what? Elliptic paraboloid, cone, and sometimes ellipsoid. None of these show up. Even if they show up, there is no need to graph these. But make sure you know how to graph elliptic paraboloid, cone, and ellipsoid. Those are, they show up, okay, but not these. So what is the last one? Are we done yet? Almost. The last one is called hyperbolic. Hyperbolic paraboloid. Paraboloid. Wow, these are like outer space kind of names, huh? How did they come up with these names? Hyperbolic paraboloid, commonly known as saddle. This is the most difficult graph you can get your hands on. So it looks almost the same as what? The same as elliptic paraboloid, except it has a minus. Okay. If this guy was plus with a z to the first on the left side, then the graph would be a bowl of soup, you know, elliptic paraboloid. But there is a minus, so it's called hyperbolic paraboloid, which commonly known as saddle. Is it easy? Not really, but let's give it a try. Graph, let's say, oh, you ready? Z is equal to negative x squared plus y squared. Okay, so notice C is 1, A squared is 1, B squared is 1. Still matches the description of the equation. Okay, let's find the cross sections. Okay, of what? On XZ plane, YZ plane. Okay, here you get Z is equal to minus x squared. Here you get Z is equal to positive y squared. Remember, these are cross sections of the surface with the planes y equals 0 and x equals 0. And the graphs or the cross sections are parabolas. These are called parabola, just like in on the floor. Okay, so what you do, you kind of what? Graph this parabola. This guy is a parabola which opens up. This guy, so this is a parabola opens up. This guy is a parabola opens down along the z-axis. There. Do you all see it? Okay. But now I have to what? See what happens when z is equal to plus or minus 1. So when z is equal to 1, I get what? Y squared minus x squared equals 1. When z is equal to negative 1, I get what? X squared minus y squared equals 1. And these guys are called hyperbola. Hyperbola. Okay. So hyper means what? Above. Hypo means under. Have you ever heard of a graph called hypocycloid? So that's under. Hyper is above. Okay, so one way to do this is graph these what? Branches of so-called what? Parabolas. And this is what I do, not that it's the best graph, but I will give it a try. Kind of like this. And then kind of like that. And that's pretty much how my shadow looks like. Incidentally, these are just what? Like this is just the parabola gets to be repeated over and over on either side. Do you all see it? Yeah, that's one. The other one is a little bit doable, which is kind of like this guy. And here is the other parabola. Okay. Then here is one of the branches of this hyperbola. Okay. And here is the other parabola, like this. Okay. So these two happens to be x squared minus y squared equals 1. And then you got these hyperbolas. And these guys happen to be what? Y squared minus x squared equals 1. And now let's try to make this look like the what? What is it? A saddle. Okay. And okay. There. So there. So these two are branches of x squared minus y squared equals 1. These two right here, you see these branches opening sideways, are y squared minus x squared equals 1. So there you have it. So this is called a saddle. Are we okay? This one is tricky, so it's not easy, but that's the best I could do. So either way is fine. If you decide to graph this just for fun of it, make sure your graph doesn't look like a butterfly. Yes, make sure it looks like a saddle. All right, so that's how you graph these. Now, if you're really, really interested to know how these guys literally look like, well, remember I gave you a site for you guys to go and explore. And where was that site? What was it called? Calc? Yeah, there it is. Plot. Okay, there it is. There. Is that right? Let's just see for laughs and giggles one of these pictures. Like, which one should we see? Let's see the saddle. You ready? So what was the equation of the saddle? It was, what was it? X squared minus y squared. There it is. I have it. And now let me just zoom out. Can you guys see it? Yeah. Let's make sure this is, let's make sure it looks like our graph, which had minus x squared plus y squared. I don't know if you guys can see it. Do you? You see the saddle? Yeah. There it is. There it is. There. How would you like to see, let's say, hyper, hyper, hyperboloid of one sheet? So for that one, you have to go to implicit form. Sorry, that's not what I want right here. Go to implicit surfaces and go x squared, what was my equation? Divided by 9 plus, what was it? Plus y squared divided by 4, was it? 4. And then minus, what was it? Minus z squared divided by, what was it? 25 equals what? 1. And here we go. Hello. What up? An error. What error? Oh, right here. Sorry. Yeah. Let me take this out. Right, what happened here? That doesn't look like it. Do I have it correctly? X squared over 9, right? And z squared over 25 equals 1.
Professor, I think you might have to use parentheses for the x squared.
Yeah, maybe, huh? Because it didn't recognize it. They don't look like anything like, you know, hyperboloid of one sheet. You're right. Sometimes it's really sensitive how you enter these guys. You're absolutely right. Let's hope for the best this time. And is that right? No, didn't put any dent. And am I in 3D mode? Am I? So what is going on? Why don't I see this? This doesn't look like it, folks. Does anyone see where did this go wrong? That doesn't look like it. And believe it or not, before the class I did it, and it sure looked fine, but now that I'm trying to show you guys, it's acting up. So, yeah, I don't know. Yeah, well, anyways, what are these? Are we on the X and Y axis, right? Yeah, let me, is that, no.
Professor, do you see how it says at like under click to insert? Yeah, that does that have anything to do with it?
I think so. These supposed to not be, yeah, no, this is not, no, this is like, if you were in a spherical coordinates, then you would use theta and rho and phi, but we are in Cartesian coordinates, so we are good, except I don't see why does it look like this.
I mean the equation below that, the z equals that equation. I don't know. Do you if that's the problem or not?
No, because I didn't put a check mark here, you see
Okay.
that? Yeah, I didn't put a check mark, and I have no idea. Let's see if we change this to plus, would that look like a ellipsoid? Wow, not even close. Do you think that has to do with what? With this guy, which is like the range of the X and Y? Could be, possibly, yes. So if I would change these guys to 6, just for fun of it, would that put any dent on my graph? Oh, there it is. Where am I? Right here. Yeah, looks like an ellipse to me. I mean, ellipsoid. Do you see it? There. But it still is not smooth. I can't believe it. I just did like 30 minutes before the class. Everything looked fine, but now it looks like a robotic kind of a uh, computer. You know, it doesn't look like a smooth football. It has rough edges. I don't understand this. But anyways, you guys play with this, so now you know where to explore these things. As a matter of fact, before I leave, I just want to show you one more idea. When you go and select the type of functions you're trying to graph, like for chapter 13, you would graph space curve, and then it would give you the parametric equations. Do you see it? In terms of t, then you would graph it. For instance, if the graph is, let's say, cosine and sine and t, let's see how the graph looks like. The graph looks like what? What is this guy called? Helix. And you can animate it. Check this out. This is like the velocity and acceleration on your curve. Do you see it? Yeah, that's the velocity and acceleration. At any given point, that's the direction of velocity, which is what? In the same direction of the motion, and acceleration, which is what? Pointing towards the, and they are not perpendicular, by the way. The only time acceleration is perpendicular to what? To velocity is when? Does anyone know?
Is
In
it
any,
in a circular motion?
yes, in a circular motion. In any other motion, as you can tell, they are not perpendicular. You see it. The only time these guys will be perpendicular would be circular motion. By the way, um, in a circle, when these guys are perpendicular, so acceleration points to the center of the circle, you know, in a circular motion, what is the name of that kind of force? Does anyone remember?
Centripetal.
Centripetal force, center-seeking force. That's exactly what happens when you exit the off-ramp on the freeway on a high speed. Everyone in your car go to one side of the car. That's why people like, kind of lean against the center of the curve. So what happens is what holds you guys in the car so you won't shoot up through the window outside because of a high speed when you make a quick turn to get off the exit is because you have the seat belt. And what makes the car not to fly away when you turn, when you get in off the exit, off ramp. So what happens? How come your car doesn't fly away? What holds the car? Remember, you just said centripetal force. What acts on the object? So technically, the car has to kind of like flip over towards the center of the curve. How come the car is still intact? Let's say you go on high speed. Let me see, what do we have here? It was friction. Yeah, which friction? Which part of the car creates friction? Let's see. What? Yes, the wheels. Yes, the tires. The tires create friction. That's why the car pretty much stays where it's supposed to. Yes, thank you guys. Thank you. Appreciate. Good job. Good job. Very impressive. Very impressive. Okay, so let's get back to our notebook here. So, is there any question about quadric surfaces? Yeah? Any question? Let me hear before I kind of go over friction with those. Yeah, my big fat tires. Yes, yes, yes. Also, have you guys seen those trucks which they are like way above the ground, big old tires, and they're like, few feet above the ground? What's up with that? What do you think? Why is it they are way above the floor? Is that like for decoration, or is it some sort of physics behind it? Anyone?
Oftentimes people like to go off-roading and stuff like that, but most of the time, if it's like a really pretty looking truck, it's probably just a show truck that they just like to look at.
Okay, but I totally understand that. But what I'm saying is there any physics behind it? Besides the fact, it's a good looking truck and impresses people. But when it's like way above the ground, what's going on? What gets affected and what compensates for that effect?
Center of gravity is much higher.
Center of gravity changes. That's why all the cars, the normal cars, they are extremely close to the ground because of the center of gravity. But when you put those shock absorbers and lift your car like few feet above, so what do you have to do to compensate?
Go slower around corners, I guess.
Yeah, go slowly, otherwise the truck will flip. No, then you have to have a fat tires, because if you have narrow tires and you put those shock absorbers like way above the ground, oh boy, you're gonna flip in like 40 miles an hour speed. So therefore, to compensate, they're gonna have a big old fat tires. Incidentally, one more idea before I launch into chapter 13. Where is the center of mass of a car?
I guess it depends on the car, but
No,
probably
any car, any car.
a little bit towards the front for most cars, probably.
Uh-huh.
Especially if it's front wheel drive, like way towards the front.
Uh-huh. It's right where the engine is. It's right where the engine is because that's the heaviest part of the car. Do you see it? So where the engine is, that's the center of mass. Your center of mass when you are standing up is somewhere close to your shoes. But the minute you bend over, your center of mass changes and comes what? Somewhere towards front of you. That's why you can't move. If you bend over, then you can't walk anymore. Why? Because you change the center of mass from somewhere close to your shoes to some point in front of you. So therefore, it really makes it hard to move. Okay, so with that little, side topic, let's get to this guy, which is called vector valued functions. So the title of this section is what is a vector value function? Any guesses? What kind of functions are called vector value? What do you think of this title, vector valued function, as opposed to real value function? That's what we have been dealing so far in previous classes. But in this class, we're gonna learn about these kind of functions, vector value functions. Does anyone care to? One that makes scalar, okay, close enough, but any other guesses? What do you make of it? Sorry?
Functions where the inputs are scalars and the outputs are vectors.
Thank you. Functions whose domain is what? All set of real numbers, numbers, but what? The range is a vector. So these are called vector value function. How do they look like, you ask? Well, in R2, they look like this. R of t equals some function of t for x component, some other function of t for y component. Notice I can also write this as f of ti plus g of tj as a linear combination of those standard unit vectors. However, in R3, I can have my my vector value function look like this: f of t, g of t, h of t, which using the standard unit vectors, this would be f of ti, g of tj, plus what? H of tk. So either notation is good. So what would be the application of these kind of functions? Well, it's mostly in motion problems. You know, when you have a moving object on what? Space curve. So these are called curves. But if you are in 3D, so we call these guys space curve. So these kind of functions gets to be written parametrically, like for instance, the first one in R2, I can also rewrite it parametrically this way. X is equal to f of t and y is equal to g of t. And let's say t goes, I don't know, from A to B. These are called parametric equation of the curve, the same curve. This is the vector form, this is the parametric form. In physics classes, these guys represent the position of a moving object on a curve, okay, where t is the time. So in R3, the parametric equation will be x equals f of t, y is equal to g of t, and what? Z is equal to h of t. So this is the parametric equation of the curve. So these are curves. and this is like curve C, and T, let's say it goes from A to B. So once again, these are called position equations in physics, which they represents the position of a moving object. Let's say this is a moving object on a curve, but in physics classes, we don't call this curve, we call it a path. So this is the path of the motion, and these guys tell you exactly what that object is at any given time. So therefore it's called position functions or position vector, okay, which is used in motion problems based on a moving object on any path, which is called curve. Okay, so a quick example of these guys, you know, I can have R of t is equal to, I don't know, t plus 1t squared, where t goes from negative infinity to infinity. Or I could have an example in 3-dimension, like let's say, what? Cosine of t, sine of t. And once again, let's say t goes from 0 to 2 pi. Incidentally, before I forget, make sure you realize the graph, what? Of the vector value functions, what? Is always, rain or shine, what? A curve. Always. Okay? Either in what? R2 or R3. Whether you are on the floor or in the space, the graph, rain or shine, is a curve. You never get a surface. So that's basically what that is. Okay, let's do a quick example so I can show you how to graph these, but you can always go to Plot 3D and graph these guys, no problem. So let's say you were asked to graph, let's say R of t is equal to 2t squared, where t has there's no restriction on t. Okay. So one way is what? Write the parametric equation of this vector value function, like so. Okay, so that would be what? The parametric equation of the curve. C stands for curve. Incidentally, why do I call this a vector value function? You give me a value of x, t, I will give you a vector. So every value of t produces what? A vector, like in this case in R2. Do you see it? You tell me where the object is 1 second after it has been it has been in motion. I can tell you the object is located as 2, 1. In other words, this is what's happening. So at 0, we are here, but 1 second later, the object is right here. 2 seconds later, the object is what? 4. So you go 1, 2, 3, 4. 1, 2, 3, 4 is right here. So every time you draw a vector, guess what? The head of that vector represents the position of the object. In a minute, we will find out after we plot many values for t, this is going to be a parabola. So that's a path. There you go. So for every value of t, that produces a vector, and the tip of that vector is a point on the path. So notice I have many values of t. Do you all see it? Yeah? So every value of t, what? Produces a vector. That's why it's called vector value function. The domain is all real numbers. I can also take what? Negative numbers. Okay, and still that would produce a vector. Do you see it? That would be like -6. That would be like 9. So every time you give me a value of t as a real value, real number, that produces a vector. What's so good about that vector? The tip of the vector is a point on the path. But now the question is, the other way is to see if you can eliminate what? Elimination of the parameter t. Here's the other way. You know, you said x is equal to 2t and y is equal to t squared. Is there any way we can get rid of the t? If so, how? Remember, t has, in this particular problem, no restriction whatsoever. Is there any way I can get rid of the t? How would I eliminate t? So here's equation 1, here's equation 2. Ready? Go. I'd like to write the equation in Cartesian form, which translates to, I don't want to have any t in my equation. So what would I do?
Solve x equals 2t for t equals x over 2, and then
So
plug.
t is equal to x over 2, call this 3. Now substitute 3 into 2. So you get y is equal to x over 2 squared, which is x squared over 4. In other words, you are graphing this equation. You and I, we both know that's a parabola whose vertex is at the origin and it opens upwards because it's positive x squared. The only problem is when you eliminate the t, it doesn't tell you the direction of the path because these guys, remember I said right here, the graph is a curve. May I also add, these are what? Orientable curves. Orientable curves, not just any curves. Excuse me, what's orientable? Orientable means they have direction. You can't just draw a parabola because you're dealing with a what? Excuse me, a moving object in what? On a path. I need to know exactly which way the object is traveling. Excuse me. So if you eliminate the t, so you get the path all right, but now you got to decide which way the motion is, what is the direction of the motion. So what do I do? Well, I don't know, select some points like t is equal to 0, go back to this parametric equation, that would give you 0.00. So at time 0, the object was here. T, let's say 1 second later, where would be the moving object be? Well, go to parametric equation, replace the t with 1. You get p is equal to 2, what? 1, right about here. So this is at t0, this is at t1. So looks to me, the object is traveling this way. So that will be the direction of the curve. So remember, when you graph what? Vector value function, you can't just graph the curve. You need to identify the direction. Excuse me, why? Because they are orientable curves. In other words, these curves have direction. Do you see it? So every time you choose a different value for y, supposedly in increasing value like t is equal to 2, 3, and so forth, or you can go negative, but make sure they're in order. So that will tell you exactly the direction of the curve. Do you all see it? Yeah? So can you guys tell me what would be the graph of this guy and what would be its direction? 2 sine of t, 3 cosine of t, where t goes between 0 and 2 pi. Did you guys want to give that a try quickly? Remember, this is your x component, that's your y component, but they're functions of t. That's how a vector value function look like. Okay. What are we doing? Nick, where are you? Are you, did you get anything? Okay. I don't see any faces, so only Nick has his video on. Nick, did you come up with anything?
Well, I watched the like video.
Uh-huh.
So I already know the
You
answer.
already know the answer. Very good.
Yeah.
So x is equal to 2 sine of t, y is equal to 3 cosine of t. Divide both sides of this guy by sine. Divide both sides of this equation by 3. Now square. So you get x squared over 4 equals sine squared. And then y squared over 9 equals what? Cosine squared. Add them up. Do I have to eliminate t? Is it possible to eliminate t in every single vector value function? No. But in this case, we could. Why? Because there is a relationship between sine squared and cosine squared, meaning if I just add these guys up, I get 1. So that's how. Is it possible to do this all the time? Not really. So what would be the graph of that? Remember, this is called an ellipse. So the x-intercept is plus or minus 2, because if you set what? Y equal to 0, you get plus or minus 2. But if you set x equal to 0, y would be plus or minus 3. So that's called major axis. This is called minor axis. So the graph, as you would guess, it's a curve. In this case, it's an ellipse, oval shape. But remember, I need a direction. So to find the direction, what? Here is your x, which was 2 sine of t. Here is your y, which was what? 3 cosine of t, correct? So pick a value like, let's say, 0 and pi over 2. At 0, x is 0, y is 3, so you are right here at time 0. Pi over 2 seconds later, you are at 2 and 0, you are here. So this would be at pi over 2 seconds later. So looks to me I'm going from here to here, so therefore, what? The direction of the curve is clockwise. You see it. So you can always, what? Extend this to, what? 3 dimension. Let's say like t negative 2t 1 plus 3t. Notice all of these guys, the functions like f of t, g of t, and what? H of t are linear. So my guess is the graph is going to be a what? A line in space. So this would be t, y would be negative 2t, z would be 1 plus 3t. I don't know if you guys remember, that's exactly the parametric equation of a line in what? In a space, isn't it? Because I can write this as 0 plus 1, 0 minus 2t, 1t, 0 minus 2t, 1 plus 3t. So looks to me the graph is a line in a space, okay? And it goes through the point 0, 0, 1, is that right? And it's parallel to, what's the direction of this line? Negative 1, negative 2, 3. So negative 1, negative 2, and what? Positive 3. If you did not recognize that, no problem. All you have to do is what? Plot some points. You know, start with 0, 1, 2, 3, 4, and then find the x. Is that right? Is that t is plus, right? So this is plus. So find x, which is t, find y, which is negative 2t, then find z, which is what? 1 plus 3t. So plot these points in what? On your three-dimensional coordinate system. But if you recognize the functions, what? which make up this vector value function are linear. So you could have guessed, oh my God, this is just a line. Goes through this point right here, 0, 0, 1, and it's parallel to this vector, which is 1, negative 2, 3, 1, 2, 3. It's parallel to this vector. Okay, so I'm gonna just go ahead and what? Graph the line. Do you all see it? The only problem is, what is the direction of the line? I don't know. Pick a point, pick a value for time. What is x? X is 0, y is 0, but z is 1. So it looks to me at time 0, the object was there. Where is the object 1 second later? Well, it's at 1, negative 2, what is this? 4. Where is that at? That would be 1, negative 2, what? 4, somewhere out here. So looks to me this is where the object is at t seconds later. So looks to me this is the direction. So the object is going upwards. Do you see it? And it goes, right? So either plot points or in 2-dimension try to eliminate the parameters so you can recognize. But if you decide not to eliminate, then what? Make a table and see how it goes. Worst scenario, then go to what? That app and see how the picture looks like, correct? So I could also have what? What was it? The graph of what? Helix. So that will be like t goes from 0 to 2 pi. And you know how the graph looks like. So these are all space curves. So the graph of this guy kind of looks like this. So that's called helix. Okay, so these are space curves. All right. So what is the domain of these kind of functions? The domain of vector value functions, vector valued functions. How do you find the domain of these guys? Well, in R2, what? The domain would be what? If you have, let's say, R of t, which is f of t and what? G of t. Okay. Or you can write this as f of ti plus what? G of tj, correct? In 2D, the domain of what? Of this vector value function is equal to all values of t such that is the intersection of the domain of f and the domain of g. In other words, you have to find common values, which what? Makes these two functions defined. Case in point, let's say r of t is equal to, let's say, natural log of t and e to the t. Okay, what would be the domain of this vector value function in R2? Well, this is my f of t, this is my g of t, isn't it? So now, what's the domain of f of t? Does anyone recognize the domain of natural log of t? Let me see what we have in the chat. Yes. Do we? What is the domain of natural log of? Oh, you said 0 to infinity. So what you're saying is this would be like what? All values of t such that t is greater than 0, not equal to 0. Equal to 0 will blow up the natural log. What's the domain of g of t? Well, looks like anything goes. So this is how you show real numbers. So this notation means is an element of. So it's a member of, and this notation is real numbers. In interval notation, I can say domain of f is what? Is 0 to infinity. Domain of g is what? Negative infinity to infinity. So the question is, what is in common? Well, graph these on a number line. So 0 to infinity, there it is. This is the domain of f. Negative infinity to infinity, so the arrow goes both ways. This is the domain of G. But where exactly these guys kind of intersect? It looks like they intersect from here and onwards. So what is the conclusion of this problem? The domain of R of t is just from what? 0 to infinity. That's the domain of this function. So you gotta find the domain of individual, graph the domains, look at the arrows, see where they intersect, you know, where they have in common. So if this guy was in like what, 3-dimension, then you would what, find the domain of F, G, and H, draw what, 3 domains on your number line and see where they cross. That would be the domain, yeah? The reason I'm trying to wave my hand on that part is because I like to, before we run out of time, like we got like 5-10 more minutes left, is to show you how to find limits of vector value functions, vector valued functions. In other words, what if someone says, hey, here's a vector value function, let's say in 2-dimension, could you please take the limit of R of t when t approaches to, let's say, a constant? How would I do that? How would you take a limit of a vector? Okay, any guesses? Yes.
You take the limit of each function individually.
Exactly. Notice the answer is still as a vector. But as you mentioned it correctly, you take the limit of each individual function as what? T approaches to A. But the answer is still as a vector. Okay. Case in point, let's say R of t is equal to, let's say, oh, I don't know, 3t. And then this guy is like, let's say, oh, I don't know, let's say 2t over, let's say, t plus 1. And let's say this guy is like t squared. And we would like to find the limit of R of t when t approaches to 1. What would that be equal to? All right. Well, as you can just guess, the limit of R of t when t approaches to 1 would be the same as taking the limit of these individual what? Components. So that would be like take the limit of this guy, limit of 3t when t approaches to 1, limit of 2t over t plus 1 when t approaches to 1, and limit of what? T squared when t approaches to 1. But the answer is still a vector. So the answer is 3, what is this? What is this? 2 over 2, which is 1, and that guy is 1. So sorry about the scratch. So therefore, the answer is 3, 1, 1, which is the same as saying 3i plus 1j plus 1k. So either you write it as linear combination of I, J, K, which this is how they write it in engineering classes, or you use this, which is called square brackets. But whatever it is, your answer is still what? Vector. So if that's the case, then what? So if I have R of t, so I'm going to continue this next time, of course. If R of t is what? F of t, G of t, how would you take the derivative of these what? Vector value functions? So this is called derivative. Okay. Remember, I have a very elaborate examples on the videos, but I'm just trying to hit the highlights here, and we also running out of time. What do you think? Derivative of vector value functions. Not including 0, derivative each component. Just like limits, You're right. Take the derivative of each component. So this would be derivative of what? F of t, comma, derivative of what? G of t. But the answer at the end of the day is still as a vector. Do you see it? I'm gonna derive this next time for you guys to see what's going on. Where is this coming from? But for now, suppose we finish today's lecture with, let's say, this guy. Remember that helix guy? Incidentally, depending where T is, then the helix will open along that what? Axis. In this case, T belongs to the Z-axis, so the helix goes like this. If the T was what? Right over here, then the helix will roll over or spiral over what? X-axis. So depending on that. Question, what is d derivative of r with respect to t evaluated at t is equal to, let's say, pi over 2? Okay. So, as you guessed it, first let me take the derivative of the vector value function, which is just derivative of each component. So that will be minus sine of t, cosine of t, and 1. Correct? Now they want me evaluate the derivative at pi over 2. Sine of pi over 2 is 1. Cosine is 0. So there goes the final answer. Do you see it? Right? Yeah, do you all see it? That's what we're gonna do. Next time I'm gonna show you how to find the equation of the what? Tangent line to a space curve. The equation of a tangent line to space curve, and what do they mean by so-called unit tangent vector? Unit tangent vector. So this is one out of 3 important vectors in motion. One of them is called unit tangent, the other one is called unit normal, and the third one is called unit binormal. So these are important vectors in any motion problems. So we will talk about these in details when we meet up next time. Thank you so much, guys, for participating tonight's lecture. Have a good night. Have a great weekend. Stay safe. And I will see you all next time. Thank you, guys.
Thank you, Professor.
Thank you.
Thank you,
Have a good
Professor.
night, guys.
Thank
Take
you.
care. Take
Thank you,
care.
Professor.